Okay, now I want to switch gears a little bit and talk about accuracy and precision. So let me define these two terms first, and then we'll spend a lot of our time showing you how to compute measures of accuracy and precision. So first of all, accuracy is the degree of closeness of measures of a quantity to the true value of that quantity. So in other words, if you want to compare an experimental value that you got to like a gold standard or a true value, that would represent like the accuracy, how close your experimental value is to the true value. So in this class, accuracy is going to be measured by computing something called the percent experimental error. Okay, and in a little bit, I'll show you how to compute that. Precision is the degree to which repeated measurements show the same results, right? So it's sort of like a measure of the variability. And in this class, we're going to measure precision by computing something called the percent relative average absolute deviation, which I abbreviate usually as PRAAD. So PRAAD is percent relative average absolute deviation. Okay, one thing I should mention is if you have older editions of our lab manual, or if you're watching older videos that I have created, then this measurement used to be called the percent experimental accuracy. So you may still see that in some of the videos where we're actually trying to get a measure of precision, but we're computing something called percent experimental accuracy. So because that name sort of conflicts, it's really not a measure of accuracy, it's a measure of precision. I decided to change the name and call it PRAD instead. But it's really the same calculation. Okay, it's really you're just calculating the percent relative average absolute deviation. But I think this is a better name so that it's clear that this is really a measure of precision. Okay, but you may still see this in some of the videos. You may see this in some of um, the old lab manuals, old lab handouts, where it's called percent experimental accuracy. So just so you're aware of that, it's nothing more than PRAD. All right, another definition that we need to know is resolution. So basically, the resolution of an instrument is defined to be the finest to which a measuring instrument can be read. So, for example, one of the first labs that we're going to look at uses what's called a vernier caliper to measure length, and it can be read to two decimal places. So therefore, its resolution is going to be 0.01, and it happens to be in centimeters, right? So 0.01 centimeters, right? Basically, it represents the resolution is like the smallest length that can be measured with the vernier caliper. Now, usually, when individuals want to demonstrate the difference between accuracy and precision, they use this bullseye analogy. So I think it's good. So let's like sort of quickly walk through this. So in this case, I have a bullseye, like a target. I have my data points here. So these black dots are my data points. And if you notice here, if you were to sort of take an average of of these data points, it's probably going to be like outside the center here, somewhere maybe in here, right? An average, and they're sort of spread out, right? So the fact that the average of those data points is not right in the center, that indicates that you have low accuracy. And the fact that there's a lot of variability, right? They're spread out, they're not really clustered, that represents low precision, right? So this would be an example of low accuracy, but not too bad. It's probably just a little bit outside and low precision. To the upper right here, this is certainly low accuracy, right? Because the mean would be like here when the true value is right in the center here. So definitely low accuracy, but high precision because there's little variability here, right? These are all clustered together. So there's little variability. That means you have high precision. Here we have an example where we have high accuracy. The mean of these is pretty much right in the center. And I would say maybe, moderate precision, right? Because it's low, maybe moderate, because they're still spread out somewhat, right? They're not really well clustered here. And in the bottom right here, this would be an example of the best case where we have high accuracy, the average is like right in the center, and in high precision, they're all clustered right in the center together. Okay, so high accuracy, high precision. Okay, so how do we measure how do we compute measures of accuracy and precision? So let me start with the one that's a little more difficult to calculate and just requires a little more effort, and that's calculating PRAAD. So remember that PRAAD stands for the percent relative average absolute deviation. And it's really a measure of precision, right? It's a measure of the variability. Okay, so here's the example. Actually, I'll go to the tablet in a second to show you this so we can just do it more carefully out mathematically. So let's say I'm measuring the length and width of a rectangular object, right? This could be a board or a table. And let's say I measure the length 10 times, right? So these are my 10 measurements of the length. I measure the width 10 times. And notice that there's some variability here, right? They're not exactly the same. There's some variability here. So in order to measure or to get a measure of that variability, I'm going to compute the PRAD for length, the percent relative average absolute deviation for length, and I'll do the same thing for width. Okay, the first thing that you should be aware of is the resolution of the instrument. So notice that if you just by looking at the data here, these are all to 1 decimal point. So that means the smallest measurement that we could make with this instrument would be zero point 0.1, 0.1 centimeters, right? Because it's 1 decimal place. So that would be the resolution of the instrument, right? 0.1 centimeters. Okay, so let me go to the tablet now and actually walk you through carefully how to calculate the PRAD for length. Okay, so here I have the 10 measurements of length written out in that column. The first thing that you need to do in order to calculate PRAD is you need to find the average of those values. So in this case, I need to find the average of these 10 values. So how do I do that? I simply add up the 10 values and divide by 10, right? If you do that, you're going to get the result of 8.14. However, and this is really important, we have to round that to the resolution of the instrument. So in this case, since these lengths are all to 1 decimal place, we have to round this to 1 decimal place. So if I round this to 1 decimal place, we're going to use the usual rules, right? I look to the right of the tenths place where I want to round it to. I have a 4 since it's less than 5. I keep the 1 in the tens place and then chop off the 4, right? And if it were 5 or higher, then I'd round up. So in this case, this simply is going to become 8.1. So that's going to be my average length. Okay, the next thing that you want to do is you want to create the second column here. The second column is what's called the average absolute deviation. And what that is basically how far each value, so like how far each of these values is away from your mean. So to calculate that, what you do is you take each value, so I'll start with 8.2, I subtract the mean, 8.1, and then since I want the absolute value of that, I need to take the absolute value of that difference. Well, we know 8.2 minus 8.1 is zero point 0.1, and an absolute value of positive zero point 0.1 is still positive zero point 0.1. So this will be 0.1. Then let's do a few more of these. So second one, I would take my data value, 8.1, subtract the mean, and then take the absolute value of that. Well, that's just going to be 0, right? Absolute value 0 is still 0. The next I have 8.0 minus 8.1. So that actually would be negative zero point 0.1, but then when I take the absolute value of that, I'm going to get positive zero point 0.1. And in many cases, you don't even need to do the math out. You don't need to do the differences in absolute value. You can just do this in your head. You can do the math in your head. So for instance, the next one, since I have 8.2, how far away is that from 8.1? Well, it's going to be zero point 0.1, right? So the next absolute deviation also be zero point 0.1. Then how far is 8.3 away from 8.1? It's going to be zero point 0.2 away. Then 8.1 is 0 away. Then 7.9, it's less than 8.1, right? But remember, it's absolute value. So that's also going to be zero point 0.2 away. Then I have 8.0, which is zero point 0.1 away, 8.4, which is zero point 0.3 away, and then 8.2, which is zero point 0.1 away. Okay, once you have all of those absolute deviations, you want to average them. And when you average them, you're going to again round to the resolution of the instrument. Okay, so if we average these, we're going to get like 0.12. So if I add those values up and divide by 10, I'm going to get 0.12. But again, I need to round to the resolution of the instrument, which is one decimal place. So this is going to be 0.1. All right, this is an important value here. This is called the average absolute deviation. Okay, it's kind of like for those of you who have taken statistics, right? One measure of variability might be standard deviation. This is sort of the same, except in order to make all the values, all the differences positive, we're just taking absolute values instead of squaring them. With standard deviation, you have to square the values. So it's similar to that, right? Just another measure of variability. Okay, now when we compute PRAAD, so like the last step here to compute PRAAD, we're going to basically do like a relative calculation here. You're going to take, so let me write this out. I want PRAAD, so percent relative average absolute deviation for length. It's going to equal my average absolute deviation, which is zero point 0.1, divided by my average value, in this case, my average length, and then times 100 to make it a percent. So it's always the average absolute deviation divided by your average value, and then times 100 just makes that ratio a percentage. Okay, so if you do that, let me just check to make sure I'm getting the correct answer here. It should be like 1.2%. So this will be 1.2%. So that is my PRAAD for length. And the lower the better, right? A lower PRAAD means that you have less variability. So we have less variability in the length there. Okay, so that's all there is to it. First, let me review this quickly again. First, we find the average, right, of our values. So I found the average length, 8.1. Then I find all the average absolute deviations, how far each value is away from your mean, from your average. So zero point 0.1, zero point 0.0, zero point 0.1, so on. I average those absolute deviations to come up with an average absolute deviation. And then finally, to compute PRAAD, I take the average absolute deviation divided by my average value, by my average length in this case, times 100. And that gives me my PRAAD. So that's my measure of precision. Okay, let me go back to the handout. Okay, now notice we could do the same thing for width, right? I have my 10 measurements of the width. I could average them, round to, in this case, one decimal place, right? The resolution of the instrument, I would get 3.2. Find all of my absolute deviations, average them, round to one place. Again, I happen to get zero point 0.1. And then if I take zero point 0.1 divided by 3.2 times 100, that's going to give me 3.1%. That's my PRAAD for width. So 3.1%. Okay, what else might you want to do with this information, with this data? Well, since we're measuring the area of a rectangle, right? We have the length and width of this particular rectangular object. One thing we could certainly do is we could calculate the area of the rectangle, right? And remember, to calculate the area of something, you simply take the length times the width, right? The formula for area is length times width of a rectangle. And in this case, I would take my average length, 8.1 centimeters, times my average width. I'm just using my average values. If I multiply them, I'm going to get 26. And then centimeters times centimeters gives me the units of centimeters squared for the area. Okay, so it's 26 centimeters squared. Notice here, actually, I was also paying attention to significant figures where my length had two sig figs, my width had two. So when I multiply it, my answer has to have um, the minimum of them, but they both have two. So the answer also has to have two significant figures, and it does. So 26 centimeters squared. All right, now what if we want to calculate the PRAAD for the area itself? So we know the PRAAD for length, that was 1.2%. We know the PRAAD for width, right, 3.1%. Now let's say we want to calculate the PRAAD for the area. So notice that area is an equation that involves length times width. Okay. Actually, let me jump over to the tablet for a second to explain this part. Okay, again, so if I want to calculate the area, we simply plug in our average values, right? So remember, this was 8.1 centimeters, and I multiply it by the width, which was 3.2, I believe. Yeah, 3.2 centimeters. And that's going to be 26 centimeters squared, right? So that's the area. To calculate the PRAD for area, here's going to be the rule, okay? And th this will be true for just about everything that we calculate in lab, actually. If you have an equation, right? So in this case, I have this equation for area that involves either multiplying variables or dividing. This is true for multiplication or division. In this case, we're multiplying two variables together. So I have an equation, right? I'm multiplying two variables together. If I want to calculate the PRAD for this dependent variable here for the area, and I know the PRAD for length and I know the PRAD for width, which we do in this case, the rule is, well, if I multiply those variables, then to calculate the PRAD for area, I have to add the respective PRADs. So the rule is I would add the PRAD for length plus the PRAD for width. And again, that's going to be true whether we multiply variables or divide variables. You're going to add the respective PRADs. Okay. This is a little complicated to explain. You need to know some calculus to explain this, but it turns out that this is true. If you add those, you can think of it as like sort of adding the errors. That's how the errors propagate. So if you add the PRADs, you're going to get the PRAD for the dependent variable. So in this case, remember the PRAD for length was like 1.2%. And the PRAD for width, I think it was 3.1%. So if I simply add those together, I'm going to get 4.3%. That would be my PRAD for area. Okay, so as long as you remember to add the respective PRADs, basically that'll handle every situation that we meet in lab. And I have that in the handout here, right? So the PRAD for area is the PRAD for length plus the PRAD for width, right? 4.3%. Okay, another really important thing. It turns out that PRAD can never have a value of 0% because we always assume that there's some error associated with the measuring instrument itself. It can't be perfectly accurate, right? It can't be perfectly correct with no error whatsoever. So here's an example of what you would do if you're going to get a PRAD of 0%, like how you would handle that, because this will come up in class for sure. Let's say we again measure the length 10 times, right, of this rectangular object. And let's say this is your data now. So here's the new table here. So notice that almost all of these are the same, right? 8.1, 8.1, 8.0, 8.1, 8.1, 8.1, another 8.0 here. Most of them are 8.1. So if I go to calculate PRAD, I would average these first, round to one place. Of course, I'm going to get 8.1. Find all my absolute deviations, which obviously in this case, most of them are going to be zero, right? The only two that are not going to be zero is the one associated with the 8.0, 8.0. Those are both going to be 0.1 for the absolute deviations. But notice here, if I average these and round to one place, right? First of all, if I average these, I'm going to get 0.02. But if I round to one place, I'm going to get zero point 0.0. And if you just plug into the PRAAD formula, that would be zero point 0.0 divided by 8.1 times 100, which I think I did here. Yep, right here. I'm going to get 0%. And we just said for PRAAD, you cannot have 0%. We cannot get 0% because there's always some error associated with the measuring instrument itself. So how do I handle this case? Well, it turns out that whenever your average absolute deviation, if this is ever less than the resolution of the instrument, then you must default to the resolution of the instrument for this value. You must use at least the resolution of the instrument of this value, which in this case, remember, the resolution is zero point 0.1, right? 0.1. So to correct this, I would simply take zero point 0.1 as my average absolute deviation divided by my 8.1 times 100. And in this case, I'm going to get 1.2% again for my PRAAD. But notice now it's no longer 0%. So this will come up if you have measurements that are basically the same or very nearly the same, right? You just have to remember you have to use at least the resolution of your instrument here for your average absolute deviation. Okay. Um, So that's it for PRAAD, right? Remember, that was the measure of precision. To calculate a measure for the accuracy, we're going to compute what's called the percent experimental error. This calculation you're probably more familiar with from other science classes you may have had, and it's a much easier calculation as well. So let's say we carry out the experiment, which you guys will be doing the first week of class, or maybe the second week, depending on what lab you're in, where you're measuring the density of a small aluminum cylinder. And let's say you go through the experiment and you find the value to be 2.6 grams per centimeters cubed, right? So that's your experimental value, 2.6 grams per centimeters cubed. Then you look this up in a handbook or you Google it, right? Or ask AI to give you the value. And let's say the accepted or predicted, or sometimes I use the word gold standard value for the density of aluminum is 2.7 grams per centimeters cubed. So basically what you want to do with this calculation is you want to compare your experimental value to the gold standard predicted accepted value, right? How close were you to the gold standard predicted value? Okay, so that's when we would compute percent experimental error. Calculation is really straightforward. All you have to do is you take the difference between your value and the predicted value. Again, I say predicted here, but remember this also means accepted or gold standard value. Sometimes we even use the word theoretical value, right? I kind of use all those words interchangeably. So I would take my experimental value, 2.6, subtract the predicted or gold standard value, 2.7, and then it doesn't even matter exactly how you do this difference here because you're taking the absolute value of it, you're making it non-negative. So that will be zero point 0.1, right? It'd be negative zero point 0.1, then absolute value makes it zero point 0.1. And then I divide by, this is important, you want to divide by the accepted predicted or gold standard value. So I divide by the 2.7 and then times 100. In this case, I'm going to get 3.7%. So again, the lower, the better, right? A lower percent experimental error means that your experimental value was close to the gold standard, to the predicted value or the gold standard value. Okay, so lower is better. And for percent experimental error, it is okay if you get 0%. In fact, that would be great. That means your experimental value would be exactly what the predicted accepted gold standard value is. Okay, so for error, it's okay to get 0%, just not for PRAAD. It's only PRAAD that we have to worry about where we can't have 0% for an answer. But for percent experimental error, it's fine to get 0%. In fact, it's really good if you get 0%. Okay, and then the last page here we'll talk about when we talk about this particular lab itself. So you can kind of just look at this. This is when we measure the density of the aluminum cylinder, but I won't discuss it in this particular video. All right, hopefully that was helpful.